All right, so we are now ready to analyze limits analytically. In particular, we're going to be looking at limits of functions at values of x equal a, where the function is not necessarily continuous. We know if it is continuous, there's nothing to do. Well, from the last video we were going over continuity. We saw the neat thing about that was that I can simply plug in, right, substitute a in for x and evaluate it for all of our basic functions. We did see one exception with the greatest integer function, but there, for most part, we are good with the functions we deal with. So the problem comes with when we get at what we call indeterminate form. So what do we mean by indeterminate form? So we say a function has an indeterminate form at x equal a if when we evaluate the function at x equal a, in other words, we plug it in, a is some number, some fixed value, then we get one of the following forms. 0 divided by 0, infinity divided by infinity, infinity times 0, or infinity minus infinity. Now, none of these forms really make any sense as a numerical quantity. I cannot divide by 0 and get a result. But remember, this is the form, we say, of the limit. And when we're taking the limit as x approaches a, we're guaranteed that x is never equal to a. Okay? But when I plug in exactly x equal a, and I get one of these forms, obviously the function is not continuous at a. Otherwise, I would be able to get a real number. We're mainly going to be focused on this indeterminate form, 0 divided by 0, in this lecture. We will look later at infinity divided by infinity and infinity times 0. By the way, some of you might say, well, isn't anything times 0 equal to 0? Well, be careful. This is the form of the limit. We're not evaluating quantity here. Infinity is not a number, so I mean you can't multiply something times infinity. And again, this is what we're approaching, really. This is what the limit is approaching. In other words, we'll talk about this later, but I have a product of two functions. One function's getting unbounded, right, more and more towards infinity, as big as it possibly can get. The other function's getting closer and closer to 0. That's what this means. We will look at an infinity minus infinity case. And again, this is not necessarily 0. We will talk about that. And there's other indeterminate forms we will look at later in the course. We'll kind of come full circle with limits towards the end of the course with a nice little rule for finding the value of a limit. Now, when a function behavior exhibits this sort of indeterminate form, we call that function indeterminate at x equal a. And as I said, such functions are not continuous, and we need a new strategy for finding the limits analytically. Now, keep in mind, we still have the strategies of numerical or graphical. We can look numerically at limits, graphically. But if we want the exact value, we want to find it analytically, and this is what we're going to do here. We are mainly going to make use of this theorem right here. And this theorem says that if we have a real number a, and we have two functions, f and g, that are equal to each other, in other words, their outputs are always equals for all values of x not equal to a. So the outputs to these functions are equal for all values of x not equal to a in some interval about a. Okay, so they're always equal in some interval. What do I mean by an interval? Well, like an open interval about a. Say, you know, if a is equal to 1, I can go a little bit less than 1, like a half, and a little more than 1, like 1.5. So the interval from a half to 1.5 would be an interval about a. Okay. So as long as this is true, of course we don't know exactly what's happening at a, but if this is true and the limit as x approaches a of g of x exists, then the limit as x approaches a of f of x exists, and these limits are equal. So in essence, what we're saying is the two functions are exactly the same for all values of x near a except possibly at a. And we don't even know if the functions are even defined at a. And that's irregardless of this theorem, doesn't matter. But the limit as x approaches a of one of our functions exists, and therefore the other function must be approaching the same limit since their values are always equal. You know, if you were doing a table of values for both of these functions, they would look identical. And so it kind of makes sense that they either both will have a limit that is the same value, or the limit will not exist. So let's look at this idea from a specific example. So let's look at this function here. Suppose we want to find out what the limit as x approaches 2 of this function is. I hope you see right away that this function is not defined at x equal 2. All right, if I plug in x equal 2, I'm dividing by 0. And in fact, it's not continuous right at x equal 2 because of that. In fact, when I plug in x equal 2, not only is the denominator 0, but the numerator is 0 as well, because 2 cubed is 8. And I get this 0 over 0 form. Okay, so how would I find the limit as x approaches 2 of this? I cannot simply plug in and evaluate like I can with a continuous function. So I can simplify this expression though. And I'm going to simplify it using the difference of cubes formula. I think we've talked about that if you've seen the video on factoring, and I've rewrote it here for your convenience. Okay, so notice up top the numerator is the difference of cubes. That's x cubed minus what? 2 cubed. So if I take a look at my function f of x, I can factor the numerator. And notice x is the u and 2 is the v, because it's 2 cubed is 8. So I've got u, which is x, minus v, which is 2. U squared, that's x squared. X times 2 is u times v, or 2x. And then v is 2 squared. V is 2, and squaring that is 4. Okay. But then if we look at this, now that I've factored, hey, lo and behold, I've got a factor of x minus 2 in the numerator. And you should know we're going to have a factor of x minus 2 in the numerator. Why is that? Because when I plugged in x equal 2, the numerator was equal to 0. And for any polynomial function, if I have a 0, right, if x equal 2 is a 0 of that polynomial function, then x minus 2 has to be a factor. That's a fact that we know from polynomial functions. So I knew already there was this factor. Okay? And that might even help when you're factoring these expressions. I knew right away x minus 2 had to be a factor, because when I plug in x equal 2 to x cubed minus 8, I get 0. So x minus 2 has to be a factor. That's true for polynomial functions. That's true for polynomial functions. Okay, so what can we do now? Both the numerator and denominator have this common factor. I can cancel that out, and I'm just left with what? X squared plus 2x plus 4 divided by 1, essentially, or just that. But in order to say that this thing and this thing on the right are equal, that the thing on the left and this thing on the right are equal, we have to emphasize the fact that this is only true provided x is not equal to what number? Provided x is not equal to 2, right? Because if x is 2, well, over here, what do we get? 0 divided by 0. Well, it's just undefined, right? Division by 0 is undefined. I know we talked about indeterminate form, but that's not a real number. But over here, can I plug in x equals 0? Sorry, x equal 2? Can I plug in x equal 2? Yeah. And that's the point. These two functions, let's call this function g of x. So the function g of x, actually let's include the restriction. Function g of x defined this way for all values of x except 2, and the function f of x, the original function we had, they are equal to each other for all values of x not equal to 2. And that means the limit as x approaches 2 of g of x must be equal to the limit as x approaches 2 of f of x. Right? That's that theorem. And so what do we have? The limit as x approaches 2 of f of x is the same as the limit as x approaches 2 of g of x, which is the limit as x approaches 2 of this function here. But this function is indeed continuous at 2, and I know that because when I plug in directly, replacing x with 2, I get a number, right? I get 12. Right? So this function, x squared plus 2x plus 4, is continuous at 2, and the limit is 12. But that means the limit of our original function is 12. In fact, what would the graph of f of x look like? Okay. Well, it's exactly this function here, right? For all values of x except 2. And actually, we can make g of x be just this polynomial function here defined at 2, and we can compare the two. What would it look like? The graph is going to be what? G of x. That's a parabola, right? Opening upward. So it's going to be a parabola opening upward for f as well, except what? Right at x equal 2. I don't know where it is. I'm just guessing. Right there. There's a hole. Okay. So if this is at x equal 2. This would be the graph of the function f. And again, I don't know if I have this exactly right. There's some hole somewhere wherever x equal 2 is. I can probably figure out what the vertex is and figure that all out. But the point is there's a hole, right? That's it. Remember we talked about removable discontinuity? We can correct that discontinuity by plugging in that hole, so to speak. And how do we, what do we do when we plug in that hole? What's that graph going to look like now? That's g of x. So g of x is just this graph with the hole filled in. So they're exactly the same for all values of x except x equal 2, and that's how we can do this. So we find a function, right, that is exactly the same as our function we're trying to find the limit of, except it's going to be continuous at that hole. And so these are the types of functions that are going to give us that indeterminate form. When I take the limit as x approaches 2, and I have a hole, that's when I'm getting this indeterminate form at that hole location. Okay. All right. Let's take a look at some examples. I like to. There's sort of 3 main ways that we simplify these expressions that we're going to find the limit of. And I gave an example of this, cancellation after expanding and or factoring. We factored, remembered, and then we were able to cancel out that common factor, and then we got our other function that we can find the limit of. Another technique is rationalizing the denominator or numerator of a fractional expression, and then also simplifying a compound or complex fraction. Okay. So I'm first going to look at examples of the first type, A. And again, these are 3 main types. There's lots of other techniques we could use to simplify expressions, especially if we talk about expressions involving trig functions or exponential logarithmic functions. Okay, but let's take a look at these to get started. Okay, the first thing you want to do anytime you're given a limit problem is to see, is this function continuous, this function here continuous where at x equal what? -3, because this is the limit as x approaches -3. So you actually want to plug in -3 and see what you get. Okay. So what happens when I plug in -3? I'm just going to plug it in down here. I already know what I'm going to get, but let's just do that. All right. The bottom's a little bit easier. If I square -3, I get +9. 9 minus 3 is 6. 6 minus 6, that's 0. So I've already got a problem, right? Division by 0 is not defined. But when I plug this in up here, what do I get? 9 times 2 is 18. 18 and 15 is 33. And 11 times -3 is -33. So 33 minus 33 is also 0. So I'd like to put that in quotes. That's a form of my limit. Okay. When I say this is the form of the limit, what I mean is we're taking the limit as x approaches -3. So what are we talking about? We're guaranteed x is never -3 in this process. What are we doing numerically, right? We're plugging in values close to -3, like -2.9, -2.99, -2.999, and so on. Values getting closer and closer to -3. And so this thing is approaching, getting closer and closer to 0 divided by 0. But we're never equal to 0 divided by 0. Okay. So this is an indeterminate form. This is what the limit's approaching. But what this means now, we want to find a function that is exactly identical to this function for all values of x except x equal -3. And the way we're going to do this, in the last example, we sort of took the function aside and we simplified it. Right? We took the function aside and simplified it, and then we went back to the limit process. Okay. I'm going to do it from now on in one connected manner, that is, I'm going to keep the limit each time until I evaluate the limit. Notice once I evaluate the limit by direct substitution, there's no more limit sign, right? Here's the limit as x approaches 2. What is it? It's 2 squared plus 2 times 2 plus 4, right? Add that up and you get 12. There's no limit sign anymore. But until that point, we need to keep the limit sign up. And so what I'm going to do is I'm going to factor. And I'll give you a hint. Since I plugged in -3 and got 0 in the numerator and denominator, that means that what, x minus a -3 or x plus 3 must be a factor of both my numerator and my denominator. I already know that. The denominator is easy to factor, right? Since the coefficient of x squared is 1, there's no, is there a common factor to pull out other than 1, first of all? No. And then, so how does this factor? I need the product of these two numbers, the last numbers, to be -6, but add to +3. And of course, the only way that can happen is if I multiply it by what? Add to +1. The only way I can do that is if I multiply these two together, right? Just check it out and FOIL that out. I get x squared. The outer is -2x. The inner is 3x. That gives me the +1x. And the last gives me the -6. Here again, there's no common factor other than 1 that I want to pull out of the 3 terms up top. And so I'm going to go ahead and factor. This time, since it's a 2x, I've got x here. I know this has to be a 2x, right? And then 3 times what is going to give me 15? 3 times 5. Does this work? Did we do it right? Check out the first times first gives me the 2x squared. The outer is 5x. The inner is 6x. 3 times 2 is 6x. That's a total of 11x. There it is. And then 3 times 5 is 15. So now, this x plus 3 factor and this x plus 3 factor will cancel. It's equal to 1. And I'm just left with 2x plus 5 over x minus 2. And now, right, these are equal. I don't need to do like comma exclude x from being -3 like I did in the previous example, right? In the previous example, we had to say, provided x is not equal to 2. But we don't have to do that here because why? Because I'm using the limit sign. And the limit sign guarantees that x is not -3. When I take the limit as x approaches -3, what we're saying is plug in values close to but not equal to -3. Right? So I don't have to worry about it. And that's what you want to do when you're solving these limits, is do it this way. But you do have to keep the limit signs here. You will lose points in your support on tests and quizzes if you don't include your limit sign after the equal sign each time. Until what? Until you get to this point and say, okay, I can now evaluate. This function is continuous at -3. Because if I replace x with -3, what do I get? I get -6 plus 5. -3 minus 2 is -5. I get -1 divided by -5, which is 1/5. I get 1/5. Notice again, I don't write the limit sign anymore. Once you plug in x equal -3, there's no need to write the limit sign anymore. But you do need to keep that limit sign until you do the direct substitution. So the function 2x plus 5 divided by x minus 2 is exactly the same as our original function here for all values of x except x equal -3. And the limit of this one, though, is easy to find. It's 1/5. Therefore, our original limit is 1/5. You don't need to say anything more if you're showing support on a test or quiz, because look at these things right here. These are called equal signs. I don't know if you've ever seen those before. That's a joke. But what we're saying is, right, this thing is equal to this thing, 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 is equal to this, is equal to that, which I've boxed, right? So the original expression equals this. We found it. This is the limit. 1/5 is the limit as x approaches -3 of this function. Okay? Now you need to put equal signs to connect those statements. Okay? Keep in mind, this is just a little aside that we should always check and make sure that we're in determinate form before we go through all this hassle. Because I wouldn't have to do all this hassle if I plug in and I get something like 1/5 over here. If I plug in and get 1/5 here, my limit, I'm done. I don't have to do any work. Okay. Let's take a look at this one here. Real quick, I think you can see if I plug in h equals 0 that the denominator is 0 clearly, and 0 minus 4 is negative 4 squared is 16 minus 16 is 0. Real easy to see this is indeterminate form. So what does that mean? Does not mean the limit does not exist. That means we've got work to do. So again, write the limit. You do have to write the limit each time. Now I don't factor immediately, but I can expand this. What is 3h minus 4 squared? Well, that's going to be 3h times 3h is 9h squared. The outer and inner terms are negative 12h, and there's two of them, so it's negative 24h. And then negative 4 times negative 4 is positive 16. So please make sure you know how to square binomials and deal with polynomial arithmetic. Don't forget our minus 16. Notice the top, I can simplify. The 16 minus 16 is 0. And then what do I have? I still plug in h equals 0. I'm still at 0 over 0. But now notice there's a common factor of h up top, which I knew I should have, since when I plugged in h equals 0, I got 0 up top. If I factor out h, I'm left with 9h minus 24. And now, right, these h's here will give a ratio of 1 always, right? And so I've got it all down to what? 9h minus 24. You should put that in parentheses, right? Because if we're taking the limit of the whole thing, even though there's only one h, right, in the expression here. But now I can evaluate that by direct substitution, right? Plugging in h as 0, I get a result which is negative 24. Negative 24. Okay. Now, a little aside here, you know, this again is support. This is, you're done. No need to do anything, because as long as you've written equal signs, right, everything is equal. So don't write this, though. I see this all the time. Don't write that. That's incorrect. When you take the limit as h approaches 0, something has to be there. If you don't write anything in there, then we're assuming it's 1. And the limit as h approaches 0 of 1 is 1, not negative 24. So don't even write that, okay? Just do this and then box your final result. You've got equal signs going. That's the way you want to show your support for these. So I'm going to be looking for the algebraic support to be neatly and correctly done. That's 90%, 99%, almost 100% of what we're doing here, still pre-calculus, to evaluate these limits. Okay. We're going to stop this video. In the next video, we're going to look at some other techniques. This was canceling after expanding or factoring. We're going to look at the rationalizing and the simplifying and compound fraction part next.